Hello everyone. Today I will present my portion of our crypto asset analysis project, specifically focusing on volatility modeling and the use of the Heston model. Cryptocurrency markets have been growing explosively, but with that growth comes significant risks such as rug pulls, where asset values collapse suddenly. um, Accurately modeling volatility is critical for anticipating these events and protecting investors. So my work done is in close collaboration with Giovanni Sanchez and supported by insights from Akshat Kumar, focuses on developing rigorous volatility-based indicators that could help detect potential rug pull earlier. After my segment, Giovanni will discuss the machine learning methods we applied to classify this risk. Here's the quick overview of what I'm going to talk about today. I will go over the project context, some data engineering steps, introducing the Heston model, and draw some conclusion about the limitations and our next steps of the project. So our project sits within a broader research initiative aimed at cryptocurrency fraud detection, sponsored to deepen understanding and create practical risk indicators. We divided the project into two parallel efforts. Andrew Lay and Gregory Colonescu analyzed on-chain transaction data using SQL to pinpoint suspicious activities, while Giovanni and I concentrated on financial market data using statistical and machine learning methods. My role specifically involved obtaining, cleaning, and analyzing historical crypto asset price data and implementing advanced volatility modeling techniques. The goal was clear, is to understand whether sudden volatility shifts could reliably predict rug pulls, helping stakeholders identify fraudulent activities early enough to minimize financial damage. So for this project, we sourced the historical price data using CoinGecko API. Specifically, we targeted the market chart endpoint to obtain daily price data for each crypto asset over the past 365 days. We created two groups: rug pull coins provided via a dataset of confirmed scam tokens, and legitimate coins, which we sampled from the top-ranked coins by market cap. Each asset was labeled with an outcome, 1 for rug pulls and 0 for legitimate coins. The data collection was automated with Python using requests and pandas for processing. Rate limiting and API restrictions were handled with built-in policies to ensure smooth extraction. Once we fetched the raw data, the next step was to clean and align it. We passed all timestamps to a standard datetime format, checked rigorously for missing or malformed data points. One challenge was handling the API rate limits, which we mitigated by implementing a 30-second pause between requests. A crucial part of this phase was determining the event date. For rug pull tokens, we identified the maximum drawdown point, that is where the token experienced its steepest collapse, as a proxy for the rug pull date. For legitimate coins, there's no such collapse, so we used the latest available data point as the placeholder. For feature construction, we focused on extracting indicators that capture price behavior before the event. This included 30-day rolling volatility, calculated as the analyzed standard deviation of the daily returns, the Heston model parameters, which I will discuss in detail shortly, and maximum historical drawdown to reflect on downside risk, and the 7-day momentum to gauge recent performance. These features were designed to capture both market stability and risk patterns, essential for distinguishing between rug pulls and legitimate coins. We used a mix of the TA technical analysis library and custom Python functions to engineer these inputs. So volatility and its importance. Volatility in cryptocurrency markets isn't just a measure of price movement, it's a vital indicator of underlying market health and investor sentiment. Traditional volatility metrics often fail to capture the complexity of crypto volatility, as these markets are known for rapid sentiment-driven price shifts and market manipulation. A sudden spike or collapse in volatility could hint at deeper market disruptions, such as fraudulent activities or rug pulls. Recognizing these shifts in advance offers a substantial protective advantage. However, accurately modeling volatility requires tools more sophisticated than simple historical standard deviations or basic volatility indicators. This complexity is precisely why we turn to advanced volatility modeling techniques. The Heston model provides a powerful framework for modeling volatility dynamically. Unlike simpler models, Heston assumes that volatility itself follows a stochastic, mean-reverting process. Essentially, it recognizes that volatility fluctuates around a long-term mean but can respond sharply to sudden market shocks. Three key parameters define this model clearly. First is theta, the long-run volatility that prices revert to over time. Kappa, the speed at which volatility reverts to this long-term mean following shocks. And psi, the volatility of volatility, quantifying how erratic volatility itself can be by explicitly modeling volatility. This way, the Heston model can more accurately reflect market reality and help detect early warnings of financial instability. We choose the Heston model because the cryptocurrencies exhibit distinct volatility patterns that simpler models fail to capture. As I said, traditional approaches often underestimate the likelihood of extreme events critical in the crypto context, where sudden price collapses can wipe out investors' value overnight. The Heston model directly addresses these shortcomings by explicitly allowing for volatility spikes, which could precede critical rug pull events. Furthermore, academic research and quantitative finance literature extensively support Heston's effectiveness in modeling complex volatility patterns, providing robust theoretical justification for our approach. This choice was validated by practical results we obtained, showing improved predictive power compared to simpler volatility measures. Our methodology involved several clear structured steps. As I said, first I collected historical price from CoinGecko, focusing on identifying rug-pull events and legitimate cryptocurrencies. Next, I prepared the dataset, counted essential daily returns, volatility metrics, and then I estimated the Heston model parameters, kappa, theta, and chi's, using a method of moments approach tailored specifically for daily volatility data. Each of these parameters was computed directly from historical volatility series leading up to known rug pull events. Finally, I integrated these parameters with additional price-derived indicators, creating a comprehensive dataset used later for predictive modeling. This rigorous approach ensured our analysis remained robust and reliable. Our analysis yielded several significant findings. Primarily, we discovered that cryptocurrencies experiencing rug pulls typically displayed distinct volatility patterns compared to legitimate ones. Specifically, they exhibited higher volatility of volatility and lower speeds of mean reversion, meaning their volatility remained erratic for longer periods before collapsing. These results strongly suggest volatility measures derived from the Heston model could effectively predict financial distress. Furthermore, statistical tests confirmed these parameters significantly differed between rug pull and non-rug pull events, providing robust and quantitative backing to our intuition. These insights formed the basis for subsequent predictive modeling, strengthening the analytical framework Giovanni later implemented. While our findings are promising, our work faced several limitations. First, estimating the Hessian model accurately requires extensive and high-quality data. Missing or noisy data, common in crypto markets, can limit parameter accuracy. Second, the Hessian model parameters, while insightful, cannot alone perfectly predict rug pulls. They must be integrated with other data points, such as market sentiment or on-chain transaction patterns. Moving forward, for future steps would involve deeper integration of volatility indicators with on-chain transaction data and possibly incorporating real-time sentiment analysis. Additionally, backtesting these predictive models over a larger dataset would further validate their practicality. So in conclusion, our investigation into the cryptocurrency volatility using the Hessian model has provided valuable insights into detecting rug pull events. Key parameters, kappa, theta, and psi, have proven especially informative, revealing volatility patterns uniquely characteristic of fraudulent crypto assets. My analysis established a solid foundation for volatility-based indicators critical for effective fraud detection, and Giovanni's work will now present how we utilize these volatility features with a robust machine learning framework, further advancing our practical predictive capabilities. Thank you for your attention. I will now hand the presentation over to Giovanni, who will explain how we took these volatility indicators into machine learning models to develop predictive tools. Here are the key references supporting our methodology and analysis, particularly literature on Hessian volatility model in financial risk modeling. Thank you.